again, in a SAR, you know you are going to have capacitance like C, 2C, 4C, 8C, so on. Right? We just saw if I have a capacitance of C, to realize a capacitance of 2C, you put two of them in parallel. Right? But by this time you should know that there are no two elements that are identical on chip. So which means in practice, this capacitance might become some C hat. Now ideally if this also becomes 2 times C hat, we are set. We just want the ratio to be 2, but there can also be a mismatch here. So this can be 4 C hat plus some delta C2 and so on. So that is the next issue we'll look at, the capacitor mismatch. So let us say I have a mismatch in the capacitor values. So which means ideally my weighting factors are 8, 4, 2, 1, so on. Now it can be 8 into some 1 plus delta 1, 4 into 1 plus delta 2 and so on. Right? So what do you think might happen because of this? I mean, first of all, why did we even have the capacitors arranged in a binary weighted fashion? Why did we have 8, 4, 2, 1?
So that the output will directly correspond to the bits.
So that I can utilize only reference values.
Remember, we need to generate reference voltages like Vref by 2, Vref by 4, Vref by 8 and so on, and that is why we did this, right? Basically 8 by total was, 8 by 16, 4 by the total was 4 by 16, 1/4 and so on. So if I have it, ideally I will have this kind of a nice step characteristic where let us say this is V by 4, this is V by 2, again 3V by 4 and so on. Now what I am saying is the capacitors are mismatched. So what will happen now? This is basically going to shift here. So what is the impact finally? This is going to result in nonlinearity. Right? Again, you can.
How can we get that mismatch in the capacitor? Like we are saying capacitors mismatch.
Correct.
So what is like exactly mismatch?
I mean, what do you understand by mismatch first of all?
Like there should be variation in different capacitors. Like their area can be mismatched.
Yeah, that's all, right? The values will not be same. That's all. I mean, if you put it, you are drawing a nice rectangle like this, saying width is W, length is L, so epsilon A by D whatever. But in practice, this will not be rectangle; it will be a crazy shape. So which means you will have a lot of functions. Actually, you can understand why this nonlinearity comes if you actually look at the SAR at a block level. See, remember in a SAR, how many comparators we use in a SAR? One comparator. So if I try to draw the block diagram for a SAR, I use one comparator. I have the input. Input is compared with a bunch of reference voltages. And what determines the reference voltage I use? The previous comparison result. So basically, I look at the previous comparator output, and then I have something here that generates this. Right. Now this is basically taking a digital input and giving an analog output, and this is what is being done by a capacitive DAC. And if you look at a capacitive DAC also, right, let's say I take a simple 3-bit case. I have 4 times C, 2 times C, and this guy is always connected to Vref, right? And in the switching schemes we saw, we had put in an initial voltage of V in minus Vref across this. So which means, let us say I connect, for example, these two to ground and this to V. What was the voltage we had here? Sorry? V in minus. This is what we had. I mean, the effective capacitance connected to ground by the total capacitance. That is the reference voltage with which I was comparing the input with. So similarly, if I connected basically, I mean, I'll write it like this. So now I see that if I have 101, I mean if this is 1, I am connecting it to ground, that's all I am meaning. If it is 101, the voltage I compare with 5 Vref by 8. Similarly, if it was for example 001, which means this is all at Vref, this is ground, what will be the voltage I compare it with? It's 18 Vref. So essentially if I try to sketch a characteristic where in the x-axis I am like plotting the code, that is a digital code connecting the capacitor switches, right? If the code is 1, the corresponding bit is 1, I am connecting it to ground. And in the y-axis I am plotting the reference voltage with which I am comparing the input. If it was 001, what is the voltage? Vref by 8. If it was 010, it would have been similarly 3, it will be 3 Vref by 8. So you'll have a nicely looking linear curve like this. Fine. No. I mean, remember that in our capacitive DAC, the capacitors by default are connected to Vref, and we are switching it to ground as and when required. Right. So the digital bit, if it's 1, we connect it to ground. Right. So yeah. So this is what happens. And remember, in a SAR also, at the end of the conversion phase, if I look at it, let us say it's a 3-bit case. The voltage I get will be some D1 times Vref by 2, D2 times Vref by 4. This is what will happen, right? Where D1 can be thought of as plus or minus 1. If the input is, I mean, remember that in the first comparison you compare with 0, right? Maybe I'll explain it. See, you compare, this is a differential case. The first comparison is with what voltage? 0. So which means initially this voltage will be 0, right? So you can think of it like this, with the only information that the input can lie in this range. This feedback loop is approximating this to be 0. Now let us say it's greater than 0. What is the next voltage you compare it with? It's 1 by 2, which means this voltage will become Vref by 2. So you can think of it like this, with the information that the voltage is in this range, the feedback loop is approximating the input as Vref by 2. And this keeps happening, right? I mean, that's why I've written it like this. If D1 is plus or minus 1, basically if the previous comparison was 1, this will be Vref by 2. If it was 0, that is minus 1, this will be minus Vref by 2, and then that will keep accumulating like this. Fine? You basically have this, and then you keep adding 1/4, 1/8, and so on. Again, this is how a negative feedback loop works, right? In a functioning negative feedback loop operates in a way so that this signal kind of approaches closer and closer to the input signal, so that the error signal becomes closer to 0. In a SAR ADC, you see, if I just do one comparison, you get only this. Second comparison, I will move closer. Third comparison, say I move closer, and as I do more and more bits of comparison, I will reach closer and closer to the input. Fine. And right now, the DAC is linear, it is fine. Now let us say the capacitors are all mismatched now. Again, I plot the characteristic here. What will happen to this now? If let us say it's first, I am looking at 001. If it is 001, what will be the voltage I get here? C plus by 8C plus whatever, delta C1 plus delta C2. So is this exactly equal to 1/8 Vref? So it's going to slightly change, maybe somewhere here. Similarly, if it was code 2, it might be somewhere here. I'm just randomly drawing. Fine. So which means now if I sketch it, it's going to be some kind of a nonlinear characteristic like this. So the point to note is, if the capacitors are mismatched, the characteristic of this capacitive DAC will become linear or nonlinear. And that's why you have this nonlinearity. That's the same thing as saying that the reference voltages are kind of staggered, so the characteristic is become nonlinear. and so which means we can't afford to have a lot of mismatch in the capacitors, right? So you will have your specification of the effective number of bits. So this will tell you what is the signal to noise and distortion ratio you can have. Now you see that for a particular linearity you need, we cannot have a lot of mismatch, right? So you should choose what is the amount of mismatch I can have based on what is the linearity I need. Fine. And this mismatch is again a random quantity, so you quantify it using statistical measures. So we define what is called as a relative mismatch, that is, we see how much is the capacitance deviating normalized with respect to the nominal capacitance value. So from a given linearity specification, you will have to find how much of mismatch I can tolerate in my design. And it turns out this factor is inversely proportional to the square root of the area of the capacitor. So the moment you fix this will fix the minimum area you can have for the capacitor. So if the minimum area of the capacitance is fixed, even the minimum capacitance you can use in your design will get fixed. So this will be the minimum capacitance as, let us say, dictated by mismatch. And in all practical designs, this value will be much greater than the minimum possible capacitance you can have on chip. So more often than not, you will find that in SAR ADCs, the unit capacitance you use will not be limited by the minimum capacitance you can have on chip. It will be limited by the minimum capacitance you need to use, so that you get some level of mismatch, and that will ensure that you get the required amount of linearity. Okay. And some ballpark numbers are this. So typically you can get a relative mismatch of about 0.1%. That's very practical. And with this you can get about 10 to 12 bits of resolution. And basically in this regime, SAR is one of the most popular design choices. So anytime you want 10 to 12 bits of resolution, SAR is one of the most common choices. So which means if you want to get higher resolution, in the recent times people have also done 15-16 bit SAR. If you want to get much higher resolution, you have to do something to correct for this nonlinearity. Just sizing this will not be enough, because if you just increase the size for 15-16, it might become impractically large. So we have to do something else to actually correct for the mismatch. And again, this is a mixed signal system. You can go and do something in the analog side or in the digital side. Which might be preferred in practice, do you think? Huh? Digital is easier typically, right? And that's what we do. And again, the idea is pretty simple, right? If I just say how you can correct it digitally. So let's say look at this block diagram. So here I have written what will happen if the capacitors are not mismatched. It is properly linear, right? Now let us say there is mismatch. If there is mismatch, you know that the weighting factors are no longer 4, 2, 1, so on. It is going to be 4 into some 1 plus delta 1, 2 into some 1 plus delta 2, and so on, right? So which means even this voltage will no longer be this, or I will basically write it like this. This I will write it as 4d1 plus 2d2 plus d3 times. I just taken 8 out and written it. Okay. So if there is no mismatch, this will be the output the capacitive DAC is providing. Now if the capacitors are mismatched, what do you think will happen to this voltage? How will it change? Again, remember, if the capacitor, I write down writing 4 to 1 because capacitor values are 4 to 1, right? If the capacitors are having some mismatch, what will happen to this 4? I mean, it will be 4 into some 1 plus delta 1 plus 2 into some 1 plus delta 2 times d2 plus 1 into 1 plus delta 3 into. So, right. So I can assume that in addition to the linear portion, I have a function that takes in this linear portion and gives you this kind of voltage. Fine. So from here to here, the voltage you get this. Now remember, the negative feedback loop is a poor thing. It doesn't know anything. How it operates is this: whatever is getting fed back to it, it will try to make it closer and closer to the input voltage so that error signal becomes 0. Okay. So right now, what signal will be equal to the input voltage? Yeah, this fellow, right? So basically, I will say this 4 into 1 plus delta 1 d1, so 1 blah blah blah. This will be made equal to the input voltage V. Okay. But what we will be doing is, we will take the digital bits d1, d2, d3. At the output, we will take the digital bits d1, d2, d3. And how do we recombine it typically? This is the MSB, this LSB. How do we convert it into a decimal number? I mean, this is a 2-bit, right? I mean, this is a 3-bit thing, so how do you do it? D3 plus?
D2 times D2
plus?
4 times D2.
Now this is what you do, but the negative feedback loop is not making this to be equal to Vn. What is it doing? It is trying to keep this signal equal to Vn. Fine. So if I were to write it right, so let us say this is your actual, I mean, this is the D out you get, and the way you are recombining is this. Fine. You are taking the 3 bits and you are doing this blue portion at the output normally. But the negative feedback loop is trying to equate f of d out to be equal to Vn. So if I just take d out, that will be f inverse of Vn. So you will have nonlinearity. So if you want to get rid of the nonlinearity, what should I do to the d out? Yeah, inverse function. So what is the inverse function here? I mean, this is the relation. I want something equal to exactly Vn. What should I do? Is this clear? I mean, I have this relation. What should I do so that I get only Vn? Pass it through that function. So if I have d out, what should I do to d out? I mean, okay, right now if I take d out itself, basically I take the digital bits and do this. I see that it is equal to f inverse of Vn. But I want to get only Vn. So what should I do to d out? I just take f of d out, right? And I mean, I'm just rewriting the same thing, right? The negative feedback loop is trying to keep f of d out equal to Vn. And f of d out is essentially this thing. Okay. So to correct for the nonlinearity, if I have the bits as d1, d2, d3, how should I be combining the getting the final output as? I mean, normally how did you recombine the output? 4d1 plus 2d2 plus d3, and you saw that that is not equal to Vn, that is some nonlinear function of Vn. So how should you combine this d1, d2, d3 so that it is exactly equal to Vn? Yeah. So you take 4 into 1 plus delta 1, 2 into 1 plus delta 2, 1 plus delta 3, and then you add it. That will give you a linear version of Vn, because that's what the negative feedback is trying to do. It is trying to make this voltage, that is 4 into 1 plus delta 1, 2 into 1 plus delta 2, 1 into 1 plus delta 3 times Vref by 8 equal to Vn. So if you also do the same thing at the output, you are set.
So we can eliminate the quantization noise also.
No, I mean here I have ensured that I have ignored quantization noise, right? See the output will not be exactly equal to the in.
That's why in the first line you put it.
Yeah. So this will be plus some quantization noise that is there. Right? I mean basically it is not like the negative feedback will make this exactly equal to this, right? If you have an infinite gain, yeah, this will be equal to this. But in this case, you will have a quantization error that is there. Let's not consider that. So that's what we do in practice. We somehow estimate what is the mismatch in the capacitors you have. Once you know that, you take the digital bits D1, D2, D3, etc. Ideally, you will be doing, let us say, 2 power some n1 times D1 plus 2 power n1 minus 1 times D2, so on. This you will do if there is no mismatch in the capacitors. If there is mismatch in the capacitors, you do this. 2 power n minus 1 times 1 plus delta 2 d2. So you just change the weighting factors you have for the individual bits, that will eliminate the nonlinearity. Right? Because basically the idea is you try to do whatever the negative feedback is trying to do. Because negative feedback is agnostic to any nonlinearity, the feedback signal will try to match closer and closer to the input with quantization of suppose. So this is how through digital domain we can correct for the nonlinearity. This is what we call as digital calibration. So of course here the challenge is you have to exactly find out what is the mismatch in the capacitors. That is again different ways in which you can do. I am not doing that. But if you can get an estimate of the capacitor mismatches, then you can incorporate the same quantities here and reconstruct the final output so that you don't have this nonlinearity. I mean, hopefully, is the basic idea clear? Why you can do it? Is this point conveyed clearly? Fine. Fine. Oh, how do you do it? Is it? There are different ways. I don't want to cover it. Right? It's a completely. There is now. Every time someone will come up with something new. Right? So we can also think and see if we can come up with something new. Yeah. Cool. So that's about I'll cover for SAR. Okay.